We're ready for our 10th and final learning objective of the thermodynamics unit. In this unit, we're going to be seeing the connection between the standard delta G and the K value, the equilibrium constant value for a reaction. We're going to derive the equation that we will use first and then practice using the equation in some example problems. Begin by answering this question. We have this black equation sitting here, and in this equation, which we learned in the last learning objective, we see a connection between non-standard and standard K. We're going to let this reaction run until it gets to equilibrium, and once equilibrium is established, which one of those statements is correct? Did you say that delta G would be 0 and that Q would equal K? Well, that is correct. When we get to equilibrium, we know that the delta G is equal to 0. And the relationship between Q and K is they are both the concentration of products, or pressure if it's gases, over reactants raised to the power of their coefficients, whatever those coefficients might be. If you are not at standard state, you're not at equilibrium, then we're putting in these values wherever we are. But it's going to keep on running until it finally gets to equilibrium, and we will remove these little initial statements there, and we are now at K. So this is the correct statement. Now we're going to take this equation and we're going to do some substitution. Where we see a non-standard delta G, we'll put 0 in, and where we see a Q, we'll put a K in. This is going to give us this equation. If we take this equation and rearrange it a bit, we're going to obtain this equation. Standard delta G equals minus RT natural log of K. This equation is one that you'll want to learn. And you're going to make sure that if you're dealing with gases that you are working with a Kp. If you're dealing with solutions, you will use a Kc. And that is a must. Okay? A review of Kp is that you have to put things in atmospheres when you are obtaining a Kp. For Kc, you will put things in molarity. With this slide, we're just going to be looking at the connections between the standard delta G and the K value and the way this reaction proceeds. If we have a situation in which we're starting at standard state conditions, PA would be equal to PB, and they would both be equal to 1, okay, 1 atmosphere, because that's standard state conditions. So that's where the dashed line is located. If we look down here at the bottom, if this reaction is starting here, it's going to want to proceed towards the minimum energy. It's going to be decreasing in the direction going towards the right, in which we are going to be producing more B and less A. That corresponds with a K greater than 1. If K is greater than 1, we know it's going to proceed to products in order to get to the equilibrium. So when delta G is less than 0, the equilibrium is going to favor those products. So we have a connection between a negative standard delta G and a positive K. Up here in the top graph, we have a situation in which K is less than 1. Well, we learned in equilibria sections that if K is less than 1, the reaction has to proceed towards reactants. It's going to go this way. So it's heading in the direction of making more A and less B. The energy is going to decrease as it goes in that direction until we get to that minimum. So if we start under standard state conditions, the standard delta G would be greater than 0. The equilibrium is going to favor the reactants. It's going to proceed to the left until it gets to the minimum value there, and so the reverse reaction is spontaneous. So we have these connections between the K and the standard delta G. We look at it mathematically with this statement up here. Let's begin with a K that is greater than 1. If K is greater than 1, then the natural log of K is going to be positive. If the natural log of K is positive, we know that temperature is always positive. R is 8.314, that's positive, and then we change the sign, that's going to give me a negative delta G. Both a K greater than 1 and a negative delta G means that products are favored. It will proceed to the right in order to reach equilibrium. Once it reaches equilibrium, you will have more products. If K were equal to 1, natural log of K is 0 and delta G standard is 0, that means this reaction is already at equilibrium and the products and the reactants are equally favored. If K is less than 1, okay, if K is less than 1, let's consider this. If this is less than 1, then this is going to be negative. And if this is negative and we change the sign, the standard delta G is going to be positive, and this reaction is going to proceed towards the reactants. If it proceeds towards the reactants, then eventually it'll get to equilibrium. Once it gets to equilibrium, your reactants are going to be favored over products. Okay, so here we have this equation once again, and really this equation has one big job. If you know delta G, you can obtain K. If you know K, you can obtain standard delta G. It's its job. You have to have this in standard state conditions to go between the delta G and the K. So we're going to practice this a couple times. First one, we're going to calculate standard delta G. If we're going to calculate standard delta G, then we're going to need to know K. We have to obtain K. And the K for this reaction is known as KSP because it's the solubility of this. So we're going to obtain KSP for this reaction. Now, how are we going to obtain KSP from the information given? Well, the first thing we're going to need to know is the molar solubility. They gave me the solubility in grams per liter, but I cannot obtain a K value unless I know it in moles per liter. So that's the first thing I'm going to do. The 6.7 times 10 to the minus 3 grams per liter can be converted to moles per liter by knowing the molar mass of the silver phosphate. The molar mass is 418.6 grams per mole, and this will give me a molar solubility of 1.6 times 10 to the minus 5 molar. Now let's write the reaction for this silver phosphate dissolving in water. Ag3PO4 is a solid. We place it into water and we obtain this equilibrium. There will be 3 Ag plus aqueous and 1 phosphate aqueous. Now we're going to place some of the solid into solution or into the water, and there will be none dissolved. When they have given me the molar solubility, they are telling me the amount of the silver phosphate that dissolves, 1.6 times 10 to the minus 5. That's what molar solubility is. This is an ICE table that I'm creating here, and so for every one of these dissolves, we are going to produce 3 of the silver. And we are going to produce 1 of the phosphate. So that's the change line. Now this is a tiny amount, so there'll still be some of the solid sitting on the bottom. I would have 4.8 times 10 to the minus 5 for the silver ion and 1.6 times 10 to the minus 5 for the phosphate ion. Now the KSP we know is equal to the silver concentration cubed times the phosphate concentration, so we can just plug those E numbers into this equation. 4.8 times 10 to the minus 5 will need to be cubed, and 1.6 times 10 to the minus 5. When I multiply those values out, I will obtain a value of 1.8 times 10 to the minus 18. So that's a KSP. Well, once we know KSP, we can get delta G. We know that standard delta G is equal to minus RT natural log of K, and in this case it's a KSP. R is 8.314 joules per mole Kelvin. Temperature at 25 degrees Celsius is 298 Kelvin. Natural log of KSP, which was 1.8 times 10 to the minus 18. This will give me a delta G of 1.01 times 10 to the 5th joules per mole. Notice the kelvins cancel, or this would be 101 kilojoules per mole. In our next problem, we're going to try to obtain a value for Kp. So if we're going to obtain a value for Kp, seeing what kind of information they have below, we could first determine the delta G. And I don't just mean any delta G, we need the standard delta G. So let's obtain the standard delta G from the standard delta G's of formations. The delta G standard for the reaction that's listed up there would be 1, because there's a 1 in front of the PCl3, 1 times the delta G of formation of PCl3 plus 1 times the delta G of formation of Cl2 minus, so it's products minus reactants, 1 times the delta G of formation of PCl5. So let's plug those numbers in. PCl3 was a negative 286 kilojoules per mole. They didn't give it to me for chlorine, but delta G formation for any element is 0, element in its standard state. And then we'll subtract the delta G formation of PCl5. We're going to subtract a negative 325 kilojoules per mole. This is going to give us a value of 39.0, it's a positive value, 39.0 kilojoules per mole. Now we're ready to obtain K. We know that standard delta G equals minus RT natural log of K. Let's solve for natural log of K first. Let's divide both sides by negative RT. So negative delta G over RT is equal to the natural log of K. That's a natural log. Doesn't look like a natural log. Let's make it look like a natural log. Natural log. Okay, so now let's plug our numbers in. Because R is in joules per mole Kelvin, I'm going to put delta G in joules. So that's going to be a negative 39,000 joules per mole. 8.314 joules per mole Kelvin, and temperature, 25 is 298 Kelvin, is equal to the natural log of K. This will give me a value of negative 15.7. Now to obtain K. If this is true that we see here, how do we get K? I want to move up to this little space up here and do it in red so we can keep track of it. The natural log of K is equal to negative 15.7. We need to take E to both sides because that'll cancel the natural log and leave me with the K. This is equal to 1.5 times 10 to the minus 7. Now, since these are gases, I know that this is going to be a Kp value that's obtained, and now we have our answer. So these two example problems get me between the standard delta G and the K. The last thing we want to look at is a relationship between temperature and equilibrium constants. If you recall way back when we first started talking about equilibria, we said that K changes with temperature. And up here in this space at the top, we'll talk about that connection. If we had a reversible reaction like A going to B, we learned that whether or not it's endothermic or exothermic will affect the value of K. If the reaction is endothermic, okay, and we were to raise the temperature, we know that this would shift the reaction to the right and K would increase. It would get larger. On the other hand, if we took the heat and we put the heat on the right and said this reaction is exothermic instead, okay, as we raise the temperature, what would happen is the equilibrium would shift to the left and the K would get smaller. So we saw that connection. We're going to derive an equation and see the connection mathematically here. First of all, look at this, what I've written. Where did this come from? That's the question. We see the equation. Well, this half is equal to standard delta G by one equation, and this half is equal to standard delta G by another equation. So we've just set them equal to each other. Now let's do some manipulations. What have I done here? I've simply divided by RT. Let's also multiply through by a -1. That's going to change that sign, and change that sign. Now let's do some regrouping. Let's take out the t's, and we have this. I've taken out the t's there entirely on the right-hand term, so the t has gone away. I have factored out the t in the first term, so we have 1 over t there. And when I do that, I have an equation that's in the slope-intercept form of a line. Y equals mx plus b. So that tells me that if I plot along the y-axis the natural log of k, that's a k. Ah, it doesn't look like a k, and it looks even less like a k. Let's start this equation over. Boop, 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 boop. So we take this equation in this form, we see it's in the slope-intercept form of a line. That means that if we were to plot along the y-axis the natural log of k, and along the x-axis 1 over temperature, we would get a straight line. And that straight line would have a slope equal to this. Now it's not always a positive slope or always a negative slope. If delta H were positive and it was an endothermic reaction, then the slope would be negative. If, on the other hand, it was an exothermic reaction and delta H was negative, then we would have a positive slope. So sometimes the slope would be negative, sometimes positive, but we have a relationship between the K value and the temperature. Now, anytime you have a straight line, it only takes 2 points to define that line, so the 2-point equation would look like this. But again, how T and K relates is dependent upon whether this term or this energy is positive or negative. Now, we won't do any work with this equation. I'm not going to have you do any mathematical examples of this, problems with it. I just wanted to revisit the notion of the K value and the temperature value that we learned way back in the equilibrium unit, and see that because of delta G, we can make that relationship between how temperature affects K, not just that temperature affects K. So here's a summary of all of the equations, basically, that we used in this unit. And we learned, first of all, about delta S, and we learned how to calculate delta S. Then we learned about delta G and defined it. And we have so many equations that have a delta G in it. And where students really struggle is to understand which one they should use. So as you're working through the example problems, be thinking about why is that the right equation to do, so that when you come to the assessment at the end, you'll be able to draw from the right equation and be able to work it. This is the end of Learning Objective 10, in which we have seen the connection between standard delta G and K. It is also the end of our thermodynamics unit in its entirety. So work through the problems, the practice problems that are presented to you, and then work on your assessment.